Now with the third condition, as can be clearly seen here, the condition 1 where this circle is orthogonal to the circle 1 given there in the problem, and the circle is orthogonal to the second equation given out here, and then thirdly the condition is given that center of the required circle lies on the diameter whose equation is given. So here the equation is given to be a straight line in this case. So using this straight line, let's see if we can form an equation where we know that for the circle S equal to 0, center is minus G minus F. That is, this center will be minus G minus F. And using this center, clearly, since center lies on 2x plus 3y equal to 7, that implies minus G minus F lies on this, is how we understand. That means this point lying on this line implies this point satisfies this equation. Therefore, 2 times of minus G plus 3 times of minus F is equal to 7. In place of x, I substitute minus G. In place of y, I substitute minus F, because this is assumed as x and this is assumed as y. So this on simplification gives minus 2G minus 3F equals 7, which on further simplification gives 2G plus 3F equals minus 7, which is equation 7. So I have obtained totally 3 equations, 4, 5 and 6. So therefore the intention is to solve these 3 equations using elimination method to find the 3 unknowns G, F and C. So in order to do that, let's frame all the 3 equations which we have found in the recent sessions. 3 equations in 3 unknowns, solving them through the elimination method. So initially I tried to eliminate C to get an equation in terms of G and F and then solve with this. So from 4 and 5 I try to subtract, so that equation 4, which is 4G plus 6F plus 6 plus C is negative 11, and 10G plus 4F plus C equals negative 21, which on subtraction gives me 4G minus 10G, which is minus 6G, is 21 minus 11, which is 10, is what we get. This on further simplification gives minus 3G plus F is equal to 5 when I take 2 common and divide. Dividing the whole equation by 2, each of the term reduces by half as this. Therefore, I get an equation minus 3G plus F equals 5, which I take it as equation 7. Now, I would like to solve equation 6 and equation 7. So, taking by equation 6 and equation 7, clearly I see that this can be made equal to this by multiplying 3, so that my coefficients of F are same. Therefore, multiplying equation 7 by 3, I get this equation 6, which is 2G plus 3F, which is minus 7, and this multiplied with 3 gives me 3 times of minus 3G, which is minus 9G plus 3F is 3 times of 5, which is 15. So this on subtraction gives me 2G plus 9G, which is 11G, and minus 15 minus 7, which is minus 22. That implies G is minus 22 by 11 which is minus 2. Therefore, G equals minus 2, which I am going to substitute in one of the equation which gives me F. So substituting in 6 gives me 2 times of G plus 3 times of F is negative 7. And this, on further simplification, gives minus 4 plus 3F is minus 7. That implies 3F is 4 minus 7, which is minus 3. That implies F is minus 1. So G is minus 2 and F is minus 1, which when substituted in either 4 or 5 gives us the value of C. Now that I have found the values of G and F, to find C I substitute in one of the equation. So here I have the equation 4G plus 6F plus C equals minus 11, where I substitute G equals minus 2 and F equals minus 1. So 4 times of G, which is minus 2, plus 6 times of F, which is minus 1, is equal to minus 11. And this on simplification gives minus 8 minus 6 plus C is minus 11. Minus 14 plus C is minus 11, which on simplification gives, which is 3. So therefore there are 3 values which I have obtained. Therefore G is minus 2, F is minus 1, C is 3. So these 3 values which we have found construct the general equation of circle required out here. So let's see how we can find the required equation of circle using the 3 values. So with the 3 equations, I substitute in S equal to 0 such that I get x square plus y square plus 2gx plus 2fy plus c equals 0. With the general equation, I have 2gx plus 2fy plus c equal to 0. That implies this is x square plus y square minus 4x minus 2y plus 3 equal to 0, which is the required equation of circle. So this is the required equation of circle, which cuts the other 2 circles orthogonally and which has its center lying on the diameter of the another line given in the problem. So like this, different system of circles have different conditions through which we find the answers with a similar procedure. So there are many concepts through which system of circles are connected with different procedures. Ultimately, it is the method and the concept which is to be understood more better. Radical axis is a new concept of system of circles, very much connected with the system. So what is radical axis? As we come with the introduction of radical axis, let's recap with the power of a point. Suppose if I have a circle and I have a point P, x1, y1, we have discussed in the previous session that power of a point is the distance from here to the tangent of the circle. So PA is the power of this point with respect to the circle. So using the concept of power of a point with respect to the circle, let's take 2 circles. If suppose I have 2 circles, circle 1 with center C1 and the circle with center C2. So for these 2 circles, let me say if I have a point where the power of the point with respect to this circle and the power of the point with respect to this circle is the same. Similarly, let me take one more point where the power of this point is as equal as the power of this point with P2. So if I have the set of all points in such a way the power of the point with respect to either of the circles are equal, then we say the locus of all the points which we join is called the radical axis. So radical axis is a straight line which is obtained from locus of all the points which are equidistant from the two circles. That is, when these two circles have the equal powers of either of two circles. As can be seen here, this point is equidistant with the powers, with equal powers, and hence we get a line which is called radical axis. Now let's see the radical axis for the three types of cases which we have in intersecting circles, in case of the circles. The first case is if I have these two circles which are far apart, then in this case the radical axis is a line which is equidistant from the two circles. So this line is equidistant from the two circles. If suppose I have two touching circles, then the radical axis is nothing but a common tangent. Is nothing but a common tangent. So radical axis of two touching circles is a common tangent. And radical axis of two intersecting circles is along the common chord. That is a secant, a common secant, or a common chord. So in this case the radical axis is along the common chord. In this case the radical axis is the common tangent. In this case the radical axis is a line exactly in between the two circles. That's how we understand the radical axis for the three types of cases: disjoint, touching, and intersecting. If suppose I have two circles, x square plus y square plus 2gx plus 2fy plus c equal to 0, and s dash equal to 0, and the condition is that these two circles are non-concentric because radical axis does not exist for concentric circles. We're non-concentric, then for these two circles the radical axis is given by L, that is s minus s dash equal to 0. That implies s minus s dash, which is given by is how we get the radical axis equation, which is a straight line. So radical axis is a straight line given by the equation L equals s minus s dash equal to 0, the subtraction of the two circles. Radical axis and its limitations. Radical axis does not exist for concentric circles. So this is where we need to understand the reason why the radical axis does not exist for the case of concentric circles. Why is the question. So here, if we take two concentric circles, then we clearly understand that these two are the circles with same center. Two circles are said to be concentric if they have same center. Now, for two concentric circles with one circle lying in the other and having same center, the question of the power of a point, say I want to take a point Px1, y1, and the power of a point with respect to this circle and the power of the same point with respect to this circle is highly impossible to be equal. That is, if I take PA and this is PB, any point we take in this plane, it is impossible that power of this point with respect to this circle, which is PA, will never be equal to the power of this point with respect to the second circle. And therefore, since there exists no point in plane such that power of the point with respect to the two circles, powers of the point with respect to the two circles are equal. Therefore, because of this reason, radical axis or locus of such points does not exist, is how we find the reason. Radical axis or locus of such points does not exist. Therefore, the limitation is for concentric circles, radical axis does not exist. Now let's identify the geometrical properties of radical axis. Radical axis is said to be always perpendicular to the line joining the centers. That is, say for example, I take two circles C1 and C2, circle with center C1 and circle with center C2. You suppose I join C1 with C2, then radical axis is always said to be perpendicular to the line joining the centers of the circles. Is how we identify the property. So L is perpendicular to C1, C2. The line L is always perpendicular to the line joining the centers. We cannot get a radical axis which is not perpendicular to the line joining the centers. Let that be disjoint circles or touching circles or intersecting circles. Now let me take three circles which are having the centers which are non-collinear. So for example, I take circle 1 with center C1 and circle 2 with center C2 and circle 3 with center C3, such that all three are not collinear. The condition here is that the centers C1, C2, C3 are not on straight line. They do not lie on straight line. So when the three circles with centers C1, C2, C3 are non-collinear, the radical axis defines its one of the most important geometrical property, where if I draw the radical axis of this, joining this and joining this, then the radical axis of C1 and C2 is exactly perpendicular and in the middle, which comes out to be this. This is the radical axis L1 of C1 and C2. Next, the radical axis of C2 and C3 is exactly this, which gives for L2 equal to 0. Then thirdly, the radical axis of C1 and C3 is also equidistant and here. And this is L3 equal to 0. The geometrical property here is that the radical axis of one pair C1 and C2 and the radical axis of C2 and C3, which is L2 equal to 0, and the radical axis of C1 and C3, which is L3 equal to 0, all pass through one point, which is a very important geometrical property, which states that radical axis, if L1 is the radical axis of C1 and C2, L2 is the radical axis of C2 and C3, and L3 is the radical axis of C1 and C3, then all three are said to be congruent. Note, L1, L2, L3 pass through only one point of intersection, which we mathematically call as concurrent. So they are said to be concurrent in case of radical axis. The radical axis of each of the circles are said to pass through one point, which is the radical axis geometrical property. Radical center is the point of concurrence of all the three radical axes. In this case, this is called the radical center. Which is the point of concurrence of all three radical axes. Is how we understand the radical center. So the point of intersection of all the three radical axes is referred as the radical center for each of the circles C1, C2 and C3.